Search and rescue teams are continuing their efforts to find survivors of flash floods that swamped eastern Kentucky.
Search and rescue crews continue to look for survivors in the U.S. state of Kentucky, where record flooding has wiped out entire communities.
A red alert has just been issued by the USGS, sending ripples through the scientific community after a mysterious geological formation has materialized or begun to emerge within the heart of the Appalachian Mountains. The warning is unprecedented for this region, long considered geologically mature and relatively stable. What was once the quiet domain of rolling ridges and gently eroding plateaus may now be host to something deeply active, something capable of unsettling assumptions about how the ancient crust beneath eastern North America behaves. Before we start, smash the like and subscribe buttons for more updates. The first signs appeared in satellite data that registered anomalous uplift in a zone straddling parts of Virginia, West Virginia, and Tennessee. High-resolution synthetic aperture radar imaging showed vertical displacement spanning several meters in some localized patches over a remarkably short time span. The suddenness and scale of the deformation caught geophysicists off guard. In a range whose tectonic activity today is negligible compared to the west coast or the interior of active rift zones, the appearance of a new deformation front is jarring. The USGS, interpreting the data in real time, elevated its alert status to red, signaling potential hazard. Perhaps most perplexing is that this formation is not conforming to any obvious existing fault trace. Appalachia's subsurface structure is a tangle of old faults, folds, shear zones, and metamorphic belts whose deeper architecture is imperfectly understood. But none of the mapped zones correspond cleanly with the pattern of uplift and tilt now detectable. The emerging structure seems to have punched its way upward, or at least reactivated something deeply buried, in a fashion that suggests the crust is more malleable than previously thought. Seismometers in the region have begun to detect tremors, modest but non-trivial, clustered around the margins of the uplift. These microquakes, though small in magnitude, cluster in depth between 5 and 15 kilometers below the surface, deeper than typical shallow crustal slip events and shallower than what one might expect from deep mantle processes. The spatial pattern of those quakes forms an arc around the rising zone, hinting that the uplift is being accommodated by brittle failure along its flanks even as the central region is ascending. The temporal behavior, where the tremors intensify in bursts, suggests episodic slippage and possibly fluid migration aiding the deformation. In tandem with the geophysical signals, geomorphic changes have been spotted via aerial photography. Valleys that until days ago looked placid now show subtle bending and sagging. Drainage channels have shifted course. Small springs appear where none existed. In one low-lying hollow, a shallow bulge has forced a spring to surface earlier than seasonal norms. Vegetation stress is visible in satellite multispectral imagery. Trees along one ridge show suppressed greenness, possibly due to lowered soil moisture as the ground shifts beneath them. In areas of greatest deformation, shallow fissures have begun to open, though more in the soft overburden than in solid rock. Geologists scrambling to map the area on foot have encountered telltale signs of deformation: small scarps in soil, tilting of older fence posts and man-made markers, fractures cutting bedrock near road cuts. What most surprises them is the relative coherence of the uplift zone. It is not dispersed or diffuse, but seems concentrated into a narrow, elongated zone hundreds of meters wide and extending for dozens of kilometers. The shape in plan view is reminiscent of a cryptic dome or blister, its summit not yet fully surfaced but clearly rising. Several hypotheses vie for attention. One posits that a diapiric body, perhaps molten or partially molten, originated deep in the crust and is pushing upward, deforming overlying rocks by buoyancy. Another possibility is that metamorphic fluids or gases pressurizing fault-bounded rock volumes are acting as hydraulic wedges, forcing upward expansion. A third draws on the notion of delamination. Perhaps a lower crustal slab has detached and is peeling away, causing the overlying crust to rebound upward. Each carries dramatic implications, none entirely comfortable within the known tectonic regime of the region. If the uplift is driven by molten rock, it opens the question of latent volcanism in a part of the continent long considered extinct. The Appalachians are a vestige of deep orogeny and erosion, not an active volcanic province. But if magma can find a weak path through, the consequences could be serious. Hydrothermal activity, gas venting, or even surface eruption in a worst-case scenario. If instead fluid overpressure is driving the uplift, one must consider whether this is a precursor to large-scale fault reactivation. If a locked fault plane is being forced upward, slipping along its periphery, the potential exists for a cascade of failures, or at least for stress redistribution across the surrounding crust. The red alert from USGS is not mere hyperbole. This formation is emerging in a heavily populated region. The Appalachian corridor, though less densely urban than coastal plains, includes many small towns, critical infrastructure, transportation arteries, and river systems. In the event that deformation escalates, landslides, ground subsidence, or sudden block motion could threaten roads, pipelines, water lines, and foundations. The ripple effects could be felt in the region's hydrology. Shifting ground can reroute subterranean flow, dam streams, or create new springs and seeps. Beyond immediate hazard, the implications for geology and models of continental stability are profound. Scientists have long held that the stable cratonic interiors and shield areas preserve their solidity over geologic time, and that once tectonic activity fades, reawakening is unlikely without large boundary forces. But here is a case in which localized internal forces, whatever their origin, seem enough to mobilize the crust from within. If so, then our conception of continental rigidity may need revisiting, especially in older mountain belts whose deep roots remain dynamic. This event is also a test for geophysical monitoring systems. The USGS deployed its full array of observational tools: INSAR satellites, ground GPS deformation networks, broadband seismic arrays, gravity surveys, electromagnetic probes, and magnetotelluric soundings. Early gravity measurements already reveal a subtle negative anomaly. Mass is being moved upward, leaving a slight decompaction signal. Electromagnetic anomalies suggest elevated conductivity at depth, consistent with fluids or elevated temperatures. All these lines of evidence must be reconciled into a coherent interpretation, but they also offer a rare opportunity to catch a mountain awakening in near real time. Another key concern is temporal behavior. So far, the uplift appears accelerating. Successive satellite passes show increasing vertical displacement. The deformation is not linear or gradual, it seems to gain momentum in pulses. That hints at feedback processes. As the rock rises, fractures open more widely, reducing resistance. Fluids or heat can further weaken the rock mass, and slip along marginal faults can both relieve and redistribute stress in complex ways. Whether the process will saturate, stall, or run away is an open question. From a regional tectonic perspective, this is an anomaly. The Appalachian chain formed during ancient continental collisions and has since undergone vast erosion and cooling. Any remaining heat in the crust is generally low. Yet here, in a region thought to be tectonically dormant, something energetic is at work. Could this be a relic of deep crustal heat pockets reactivating under a favorable structural condition? Or an artifact of deep mantle dynamics pushing upward? Or a combination of processes we have not yet fully imagined? The answer could reshape how geologists view ancient mountain belts globally. Public interest is intense. Local communities have mobilized. Geological survey teams, academic researchers, and emergency management agencies are coordinating to monitor the event and share information. The USGS is holding press briefings, cautioning that it cannot yet predict if or when a hazardous event, ground rupture, landslide, or venting will occur. What is clear is that the formation transcends mere academic curiosity. It tests Earth's ability to surprise us even in supposedly stable zones. As the formation continues its upward march, instrumentation is being densified. Boreholes are being planned, cores extracted, strain meters installed. Specialists in rock mechanics, fluid geochemistry, thermal physics, and structural geology have all converged on the site. They must piece together how the crust is deforming, whether it is brittle failure, ductile creep, or a hybrid. The interplay of pressure, temperature, rock rheology, fault friction, fracture networks, and fluid flow must all be teased apart. Researchers are especially focused on constraints like rock strength at depth, permeability thresholds, and thermal gradients, because these will determine whether the uplift can continue or saturate. If permeability is low, fluids may choke off, arresting the rise. If temperature gradients remain modest, brittle strength might dominate and the uplift stall. But if feedback loops dominate, the structure could breach the surface or trigger cascading slips in surrounding faults. The very existence of this formation challenges the idea that mountain belts are dead after their orogenic phase. It raises the possibility that even in ancient terrain, latent energy, thermal, fluid, or structural, can still be unleashed given the right subterranean conditions. That has deep implications for hazard assessment in old mountain chains around the world, from the Urals to the Appalachians to the ancient ranges of Europe and Asia. Geophysical models are already being updated in response. Finite element simulations are exploring whether models driven by fluid pressurization, thermal buoyancy, or mechanical delamination best reproduce the observed uplift dynamics, seismicity, and electromagnetic signatures. Some models suggest that a hybrid mechanism, fluid-assisted diapirism, best fits the data. Fluids reduce effective stress and allow rock to intrude upward slowly, aided by heat and fault slip. Others argue that a magmatic core cannot yet be ruled out, and that further temperature and melt proxies must be resolved. One of the gravest concerns is the possibility of escalation. If the uplift threatens to pierce through to shallow crustal levels or the surface, sudden collapse or explosive release of pressure could occur. Even absent volcanism, sudden ground subsidence or lateral collapse of the uplifted mass could generate catastrophic local events. Understanding the thresholds at which the deformation field transitions from distributed to localized slip is now urgent research. Yet another implication lies in energy and geothermal potential. If heat or magma is closer to the surface than expected, this might expose dormant heat sources previously unrecognized. Could a geothermal system emerge spontaneously? Could new mineralizing fluids accompany the deformation and deposit valuable ore bodies? The event thus has both hazard and resource implications. Beyond the local scale, the formation is a warning and a window. It warns that Earth's deep engine still operates even where we thought it had cooled and quieted. It offers a window on a process rarely seen in real time, the birth or reawakening of an anomalous crustal structure in ancient terrain. The implications for tectonics, risk assessment, and geological theory are vast. As the red alert pulses through the community, every passing day brings new data, new surprises, and new challenges. Whether this mysterious formation emerges into full view, whether it stalls, falters, or accelerates beyond control, is a drama playing out beneath ridges carved long ago. And as it unfolds, geology may be forced to revise long-held beliefs about the permanence of ancient mountains and the hidden dynamism still buried within. The Appalachian Mountains, stretching in a long arc from Alabama to Canada, have always been revered as one of the most ancient geological features on the planet. Their rounded summits, eroded ridges, and timeless valleys embody deep history, and until now they were thought to be locked in a phase of quiet decline. But the sudden emergence of a new and unexplained formation shatters that assumption. The red alert raised by the USGS underscores that something is happening which does not align with centuries of geological expectation. It is as though the mountains themselves, after eons of stillness, are stirring again. What makes this development so haunting is not just its physical scale, but its defiance of classification. Scientists can usually place anomalies into known categories. Earthquakes trace fault lines, uplift reflects plate convergence, and volcanic domes hint at mantle plumes. Here, none of those archetypes fit perfectly. The Appalachian system has no active subduction zone feeding magma, no spreading rift generating uplift, and no plate boundary stresses to explain abrupt motion. Instead, what has been detected resembles a buried force that has quietly grown for centuries or even millennia, now breaking through with sudden vigor. The setting amplifies the unease. Appalachia is not wilderness alone, it is a living landscape filled with communities, industries, and heritage sites. Small towns cling to ridges, highways snake along river valleys, and entire economies depend on coal seams, shale gas, and the forests that blanket the slopes. The prospect of a deep-rooted upheaval is not abstract for the people who live there. If hillsides heave or valleys tilt, homes could be displaced, roads severed, and livelihoods disrupted. A formation pushing upward from within the crust poses a very real threat to stability in the region. While the cause remains debated, the visual manifestation of the formation is becoming clearer with every new survey. Researchers flying over the region describe the outline of a bulge that stretches like a crescent against the older topography. Where the uplift has begun to break the surface, rock strata have buckled, tilting layers of sandstone and shale into steep new angles. In several places, thin sheets of rock have peeled, as though the earth were shrugging off its outer skin. Such physical evidence confirms that the process is not an illusion of instruments, but a tangible reshaping of the land itself. One of the more fascinating details emerging from field reports involves the acoustic signature of the ground. Residents have reported low, resonant rumbles at night, distinct from the sharp jolts of earthquakes. Instruments confirm that these are long-period signals, a kind of subterranean hum, suggesting fluid motion or pressure waves deep beneath the surface. These sounds mark a new chapter in understanding Appalachian geology. The mountains are not merely eroding monuments, but dynamic systems still capable of producing acoustic energy as they shift. For geologists, the phenomenon raises critical questions about how ancient mountain belts evolve. Traditionally, once collision-built ranges like the Appalachians cease uplifting, erosion dominates and tectonic quiet follows. Yet the red alert signifies that stored energy persists, perhaps hidden for hundreds of millions of years, waiting for conditions to release it. Could the roots of the Appalachians, buried deep in the lithosphere, harbor trapped fluids, melt pockets, or structural instabilities that can be reactivated? If so, this would force a reevaluation of the life cycle of mountain systems worldwide. Another implication of the event lies in how it intersects with water. The Appalachians are the source of countless rivers that feed into the Ohio, the Tennessee, and ultimately the Mississippi. If deformation continues even slightly, drainage patterns could be redirected. A small change in slope can reroute streams, carve new gullies, and dam old channels. This has profound implications for agriculture, navigation, and flood control. Engineers are monitoring reservoirs and dams downstream with heightened attention, aware that even minor shifts in upstream hydrology could cascade into larger issues for water management. The cultural dimensions cannot be overlooked either. Appalachia has long been home to deep traditions, from indigenous histories to coal towns built during the industrial boom. Land holds not just economic, but spiritual and ancestral value. When the ground itself begins to transform, it unsettles more than property boundaries. It shakes identity. Local stories, folklore, and even religious interpretations are beginning to merge with scientific discourse. Communities describe the event not just as geology, but as an awakening of the mountains themselves, imbuing the scientific mystery with human significance. On the scientific front, researchers are pressing for faster deployment of borehole sensors. Only by drilling directly into the rising formation can temperature, pressure, and gas composition be measured. These parameters are critical for distinguishing between molten intrusion, fluid-driven uplift, or mechanical rebound. If gases such as carbon dioxide, methane, or sulfur compounds are encountered at depth, it would strongly suggest magmatic or hydrothermal involvement. If, on the other hand, boreholes reveal overpressured brines and altered mineral veins, the uplift may be tied to deep-seated fluid migration. Each scenario carries unique risks, from toxic venting to ground destabilization. What excites the scientific community most, however, is the opportunity to observe a formation of this magnitude in real time. Normally, tectonic or magmatic processes reveal themselves through historical remnants or fossilized structures. Here, for the first time in Appalachia, researchers can watch a new structure grow, measure it as it develops, and track its influence on the landscape. This is a living laboratory unlike any other, and it may yield data that will revolutionize Earth sciences. The Red Alert designation also forces consideration of emergency preparedness. Schools, hospitals, and municipal authorities in the affected corridor are revisiting evacuation routes, communication systems, and disaster drills. Unlike hurricanes or floods, a geological crisis is unpredictable in its timing and form. Emergency managers must prepare for scenarios ranging from localized landslides to broader crustal shifts. The unpredictability creates a unique challenge: how to prepare populations for an event that defies precedent. The military and federal agencies are also showing interest. The Appalachian Corridor contains critical infrastructure, gas pipelines, high-voltage transmission lines, and military installations. A deformation zone expanding beneath these assets raises national security concerns. Satellite reconnaissance is being leveraged not only for civilian science, but for infrastructure assessment. Officials are keen to know whether the deformation could intersect with transport routes or energy corridors vital to the national grid. Perhaps one of the most striking aspects of this mystery is how it unites disciplines. Seismologists, geomorphologists, hydrologists, anthropologists, and even climatologists are drawn into the conversation. The event is not siloed, it is a nexus where natural science, human geography, and public policy converge. Every data set from satellite imaging to oral accounts of rumbling contributes to an evolving mosaic of understanding. The integration of disciplines may become a model for handling complex, multidimensional natural events in the future. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the mysterious Appalachian Formation, natural event or hidden threat? We want to hear from you. Thank you for watching and see you next time.